You are standing on the surface of the moon, and the ground beneath your boots is 270 degrees Fahrenheit, hot enough to melt solder. The sun hangs fixed above the horizon. It won't visibly move for hours. Take 3 steps to your left into the razor-edged shadow of a boulder, and the temperature plunges to negative 280, a 550-degree swing across the width of a doorway. There is no air to carry the heat, no breeze, no sound, nothing between you and any of it. And right now, none of that is your biggest problem. An hour ago, a monitoring satellite parked between Earth and the Sun flagged a coronal mass ejection aimed squarely at the Moon. A wall of high-energy protons is racing outward at 1/3 the speed of light. On Earth, the magnetic field will shrug this off, and nobody will notice. But you have no magnetic field, no atmosphere. The thickest thing between you and those protons is a few millimeters of spacesuit fabric and aluminium. You have roughly 45 minutes before the wave arrives, carrying enough radiation to kill you in under 6 hours. This is not a thought experiment. It is the scenario that has haunted every lunar mission architect for more than half a century, and the central reason no human being has stood where you're standing since December 1972. Every danger on the lunar surface, radiation, dust, thermal violence, micrometeorite bombardment, traces back to one missing thing. Earth wraps its inhabitants in a double shield, a magnetic field generated by convection currents in the planet's liquid iron core, and a 100-kilometer deep ocean of atmosphere. Together, they deflect charged particles, filter lethal radiation, moderate temperature swings, weather rock into smooth, harmless grains, and vaporize incoming debris before it ever touches the ground. The Moon has neither shield. Its small iron core cooled and solidified somewhere between 3 and 4 billion years ago, shutting down the magnetic dynamo. Its gravity, about 1/6 of Earth's, was never strong enough to hold atmospheric gases against the relentless erosion of the solar wind. Those gases escaped into space and never came back. Strip away both shields, and the raw physics of space reaches the surface unfiltered. That single fact, no magnetic field, no atmosphere, explains every danger on the Moon, every engineering challenge of going back, and every reason the first crewed moon mission since Apollo required more than 50 years of new science to become possible. The Apollo astronauts survived on luck. That is not folklore, it is arithmetic, and the numbers are sobering. Between 1968 and 1972, NASA flew 9 crewed missions beyond Earth's protective magnetosphere. Total time human beings spent exposed to unshielded deep space radiation during the entire Apollo program, roughly 30 days. During that window, the Sun cooperated. Solar activity was moderate. The crews absorbed elevated doses, each roughly equivalent to a few dozen chest X-rays, but nothing that triggered acute symptoms. Then came August 1972, 4 months after Apollo 16 splashed down safely and 4 months before Apollo 17 launched. The Sun produced one of the most ferocious solar particle events of the 20th century. A massive flare erupted from the solar surface, accelerated protons to enormous energies, and hurled them outward in a concentrated blast. Had that storm struck during a lunar surface mission, had the calendar shifted by just a few months in either direction, the astronauts, shielded by nothing more than the lunar module's thin aluminum hull, would have received an estimated 400 rem of radiation within hours. For context, 100 rem triggers acute radiation sickness, nausea, vomiting, and a dangerous collapse in white blood cell count. 400 rem is frequently fatal without immediate intensive medical care. 600 rem is lethal, full stop. The margin between a triumphant mission and a disaster was a few months of calendar luck, and nobody controlled the timing. The full scale of this danger only became clear in the decades after Apollo, through instruments the program never had access to. The critical data came from spacecraft stationed at the L1 Lagrange point, a gravitational balance location between Earth and the Sun, where a satellite can hold position indefinitely and keep the Sun under continuous watch. Missions like ACE, launched in 1997, and DSCOVR, launched in 2015, spent years cataloging solar particle events, measuring their intensity, their frequency, and the warning time they provide. The statistical picture that emerged was not comforting. Dangerous particle events, storms capable of delivering acute radiation doses to anyone beyond Earth's magnetosphere, occur multiple times per 11-year solar cycle. Apollo's 30 days of cumulative exposure threaded through that minefield by sheer chance. The physics is elegant and merciless. When the Sun erupts, it accelerates protons, bare hydrogen nuclei, to energies that punch through centimeters of aluminium. On their way outward, these charged particles follow the rules all charged particles follow. They spiral along magnetic field lines. Earth's magnetic field, powered by its churning molten core, creates a vast magnetosphere stretching tens of thousands of kilometers into space. Most solar protons get swept around this magneto bubble without reaching the surface. The fraction that slip through slam into nitrogen and oxygen molecules in the atmosphere, shedding energy in cascading collisions long before reaching the ground. The Moon offers neither layer of defense, no magnetic field to deflect, no atmosphere to absorb. Every proton arrives at the surface carrying its full energy. And there is an additional cruelty. The regolith below reflects and re-emit secondary particles upward. So the radiation dose on the lunar surface is actually higher than in open space at the same distance from the Sun. The ground itself becomes a second source. During a major storm, you are bathed from both directions simultaneously. Artemis missions are engineered around this reality in ways Apollo could not have been. The Orion spacecraft includes a dedicated radiation storm shelter where crew members retreat during solar events, surrounding themselves with the densest available mass, water tanks, equipment racks, supplies. Water is nearly ideal for stopping protons. Hydrogen nuclei are almost exactly the same mass as the incoming particles, meaning each collision transfers maximum energy. Real-time solar monitoring from Discover provides 15 to 60 minutes of advance warning before a particle wave reaches the Moon, enough time to seal up and shelter. Apollo had no warning network. No shelter protocol, no contingency beyond hoping the Sun stayed quiet, but radiation is the invisible threat. Apollo astronauts actually spent far more mission time wrestling with something they could see, feel, and, disturbingly, taste. Every single landing crew reported it as their worst operational problem. In December 1972, Harrison Schmitt, the only professional geologist ever to walk on the Moon, removed his helmet inside the Apollo 17 lunar module after his second moonwalk and immediately started sneezing. His eyes watered, his throat swelled shut. He described the symptoms as severe hay fever. They cleared within a day, but the cause was extraordinary. He was reacting to lunar dust. And the reason lunar dust is dangerous traces straight back to that same missing atmosphere. On Earth, particulate matter is weathered. Wind, water, freeze-thaw cycles, and biological activity gradually round sharp edges, break down reactive mineral surfaces, and coat grains in stable oxide layers. A freshly fractured rock fragment might start jagged and chemically aggressive, but within centuries, natural weathering renders it comparatively harmless. On the Moon, no weathering exists. Lunar regolith is created almost entirely by micrometeorite impacts, tiny projectiles striking the surface at 10 to 70 kilometers per second and shattering rock into fragments with nanoscale razor edges and freshly fractured crystal faces that have never encountered oxygen or water. Without atmospheric chemistry to alter those surfaces, they never change. A grain of lunar dust created 3 billion years ago retains the same jagged geometry and the same chemical reactivity it had the instant it formed. Time does not blunt anything on the Moon. The particles are extraordinarily fine, many smaller than a red blood cell, and they cling to everything. Solar UV radiation and charged particle bombardment, unfiltered by any atmosphere, strip electrons from dust grains and create intense electrostatic charges. Lunar dust does not settle passively. It leaps onto surfaces, bonds to fabric and glass, and embeds itself in mechanical joints. The damage during Apollo accumulated with alarming speed. Across roughly 80 total hours of surface activity spread over 6 landing missions, dust infiltrated suit joints and stiffened the bearings. Helmet visors were scratched badly enough to impair visibility. Equipment seals degraded, and every time astronauts brought dust into the pressurized cabin on their suits, which was unavoidable with Apollo-era airlocks, it became airborne and was inhaled immediately. Post-Apollo laboratory studies revealed the biological stakes. Working with carefully synthesized lunar regolith simulants, researchers found that the ultra-fine particles penetrate deep into lung tissue, well past the depth the body's mucociliary clearance can reach. The iron and titanium on those fresh crystal surfaces generate free radicals, highly reactive molecules that damage DNA and rupture cell membranes. The mechanism parallels asbestos exposure, but the extreme surface reactivity of lunar dust means damage likely accumulates faster. Artemis suits represent a complete redesign driven by this physics: dust-resistant outer layers, positive pressure seals that push air outward through joints to block dust intrusion, and perhaps most importantly, suit port airlocks. The suit stays mounted on the habitat's exterior, and the astronaut climbs in through a rear hatch. The contaminated outer surface never enters the living space. Every innovation exists because the Moon's missing atmosphere turns ordinary pulverized rock into a slow-acting toxin. And the same absent atmosphere spawns secondary threats that compound the primary ones. Without air to convect heat, the lunar surface exists in thermal extremes no environment on Earth can match. Sunlit regolith bakes past the boiling point of water. Shadowed ground mere meters away drops colder than the surface of Pluto. Equipment designed for one thermal regime fails catastrophically in the other. Lubricants freeze or decompose. Solder joints crack under relentless cycling. Artemis missions carry active thermal management systems that Apollo-era technology simply could not miniaturize. Without an atmosphere to burn up incoming debris, the surface is an unshielded shooting gallery. Earth's air incinerates roughly 100 tons of cosmic material every single day. On the Moon, every grain arrives at full velocity. Consider the arithmetic. A particle weighing 1 milligram, smaller than a visible grain of sand, traveling at 20 kilometers per second, a fairly typical impact speed. Kinetic energy is half the mass times velocity squared, half of a millionth of a kilogram times 20,000 meters per second squared. That gives roughly 200 joules, about the muzzle energy of a .22 caliber bullet packed into something nearly invisible to the naked eye. For Apollo's brief visits, the statistical risk of a dangerous strike was low enough to accept. For month-long habitation, it demands Whipple shields, multi-layered barriers that shatter incoming projectiles into harmless plasma before they reach the pressure hull. But here is the turn that transforms the Moon from mere hazard course into something irreplaceable. The same missing atmosphere that creates every danger also creates scientific opportunities found nowhere else within reach. Because there is no air to trap and redistribute heat, the floors of certain craters near the lunar poles, craters whose rims are tall enough that direct sunlight has never reached the bottom, have sat below negative 380 degrees Fahrenheit for billions of years. They are among the coldest places in the entire inner solar system, and in 2009, NASA's L-Cross mission proved those floors hold a treasure, water ice, delivered by comet impacts over geological time and preserved in the permanent cold. The mission slammed a spent rocket stage into the shadowed Cabeus crater near the South Pole and analyzed the debris plume with spectrometers. The signature was unmistakable: significant water locked in the regolith for eons. That ice can be split into hydrogen and oxygen, breathable air and rocket propellant manufactured on the Moon itself. The deadliest feature of the lunar environment is precisely what preserved this resource untouched for billions of years. And because there is no atmosphere to scatter or absorb light, no radio interference from human civilization on the far side, and no seismic noise from weather, the lunar surface is one of the finest astronomical observation platforms in the solar system. The danger and the scientific treasure are the same physics viewed from different angles. So the 50-year gap between Apollo 17 and the first crewed moon mission since Apollo is not a story of lost ambition or political failure, it is a physics story. 6 brief landings revealed that the lunar surface is extraordinarily hostile and that every dimension of that hostility flows from one physical absence: no magnetic field, no atmosphere. Solving the radiation problem required 30 decades of solar physics and new shielding materials. Solving the dust problem demanded advances in nanotechnology and electrostatic engineering that matured only in the 2010s. Solving the thermal and micrometeorite challenges required miniaturized active systems that Apollo-era technology could not produce. Artemis is not a replay of 1969, it is the accumulated answer to every question those first landings raised. And here is the thought worth sitting with. The Moon is 1.3 light-seconds away. You can see it on any clear night with your bare eyes. You can point at the exact spots where 12 human beings left footprints in dust that will outlast every structure ever built on Earth, because without wind or rain, nothing disturbs them. And even this world, practically next door by cosmic standards, the closest place beyond Earth where a person could stand, required half a century of physics just to make survivable for longer than a few days. Mars is more than 800 times farther at closest approach. The radiation exposure there stretches from hours to months. The dust carries perchlorite compounds that attack thyroid function through entirely different chemistry. The thin carbon dioxide atmosphere helps with a few problems and introduces new ones: planet-spanning dust storms, corrosive surface chemistry, pressure too low for liquid water but too high to ignore. The Moon is where the species proves, or fails to prove, that a world with no natural protection can be made survivable through physics understood deeply enough to engineer around. 12 people have stood on the lunar surface and looked back at Earth. From that distance, the atmosphere is barely visible, a faint luminous arc hugging the planet's curve, a film thinner than the skin of an apple relative to the diameter of the world it protects. That film, held in place by a magnetic field churning deep underground and a gravitational pull just barely strong enough to keep the gases from escaping, is the only reason anything on the surface below is alive. The Moon, silent and utterly exposed just 1 light second away, is a permanent monument to what the universe looks like everywhere that film does not exist. The next boot print pressed into that ancient dust will not be a keepsake, it will be a proof of concept for every world that comes after. Like if this was interesting, hit the subscribe for more and turn that notification bell on.